A concept that's going to come back from last week is this idea of absolute value. Last week we found this value called r, which we use to plot points on a coordinate plane. The absolute value of a complex number is the same thing as this r, and in fact we often will use the letter r to describe it. However, the more formal word, absolute value or modulus, which it'll be called when you get into a calculus course, that more formal name is often used to replace the idea of radius or r. And just as a heads up, you may see this notation as well, z representing a complex number actually placed inside these absolute value brackets. So just like with regular old numbers, an absolute value is just the distance from 0. But now it's in the complex plane. So we have to take two dimensions into account, a real dimension and an imaginary dimension. One thing that got screwed up here, that should be a little baby a. A is used to represent our real numbers in that complex plane. This guy should be a b. But now that we have that all sorted out, no harm, no foul. Again, that a represents the real part of our complex number, and b represents the imaginary part of our complex number. Finding the absolute value is the exact same formula we use to find r, and it comes from our Pythagorean theorem. So the absolute value of our complex number will just be the square root of a squared plus b squared. Again, where a is our real part and b is our imaginary part. So it's the same formula that we use for r, it's really just the Pythagorean theorem because we have built this little right triangle in the complex plane. So we're going to eventually use this idea of absolute value to help us get the polar form of a complex number. That's where this is all heading. But before we get there, let's just find a couple absolute values. Note all of these complex numbers are going to have a real part, which I'm highlighting in yellow, as well as an imaginary part that I'm highlighting in green. And actually finding these values is nothing more than Pythagorean theorem. So we want the square root of 8 squared plus 6 squared. This is one of our nice ones because 8 squared is 64, 6 squared is 36, and 64 plus 36 is 100. Well, we can reduce the square root of 100, that's one we know. It's just 10. So let's look at one that's slightly more interesting. Jumping over to number 8. So now we have negative 3. That's our real part. We'll square that. And then we want to be careful. The I is not actually a part of that b value. So for the b, all we're squaring is the negative 1. We don't want to also square the I. Keep in mind, I squared is a negative 1, and that would add too many negative 1s into this problem. So we're going to have a negative 3 squared, that's 9, and a negative 1 squared, that's 1. 9 plus 1 is root 10. Can't do any extra work with that square root of 10. That is a fully simplified radical. Let's take a look at one more just for funsies. Once again, we want the square root of our real part squared, so that's 2 squared, plus our imaginary part squared. 2 squared is going to be a 4. Negative 11 squared is 121. 4 plus 121 is 125. And that's a radical we can actually do something with. 125 you can break up into 25 times 5. The reason we would break that up over those two numbers is that the square root of 25 is something we know. So that's just 5. And the root 5 tags 11. So note that your modulus, or your absolute value, can be a whole number, it can be a radical, or it can be something like this 5 root 5, a radical that also has a coefficient. So a modulus can take several different forms. We want to be comfortable seeing all of these forms. So that's all there is to the absolute value idea. It's just finding r, like we did for complex numbers. We're just giving it a new name as it relates to these complex numbers here. So after this, we'll talk about getting the whole complex number into polar form, so stay tuned.